construction and operation of our USV was first divided into three major subsystems. The mechanical subsystem, which entitles the body of the USV, the ball capturing mechanism, and the ball disposal mechanisms, and the USV motion and the steering. The recognition subsystem, which includes the AI algorithm that recognizes the balls and sends alerts to the control subsystem. And finally, the control subsystem, which encompasses the various electronics. It receives the signals from the recognition subsystem and works to control the mechanical subsystem to perform the required action, whether it's movement or the action of the ball collection or disposal.
The mechanical subsystem was the first aspect addressed, focusing on the USV's flotation, steering, and ball capturing and disposal mechanisms. Multiple materials and shell designs were evaluated, and the final chosen design uses PVC pipes for the lower frame for flotation, with a 3D printed outer shell on top for the USV body and to house the electronics, balancing cost effectiveness with aesthetics. For the ball collection mechanism, several ideas were again considered, and the chosen design utilizes a conveyor belt with cleats to capture balls as it rotates. The size of these teeth will be tested to ensure that they effectively capture balls at the specified 6.5 cm diameter. The balls will then drop into a basket at the top of the belt, which will rotate to release them at collection sites. This method is efficient and continuously collects multiple balls as the USV moves, with the conveyor belt's constant rotation. There are two main motors with propellers, and the speed and direction will be controlled to steer the USV.
The recognition system utilizes advanced computer vision techniques implemented in ROS2 version Jazzy Jalisco and simulated in Gazebo on an Ubuntu-based environment. It provides better support for ROS2 Gazebo integration. A combination of color detection algorithm along with machine learning models will be used to identify and classify the colored balls using HSV color-based detection algorithm. It will be trained to avoid the red color balls and advance towards the other balls as per the competition regulations provided. Additionally, IMU will provide orientation and motion data for precision and stability. The robot's camera feed will then be processed using OpenCV libraries to apply color thresholding and contour detection to help isolate the ball from the pool environment. To simulate and test the robot's performance, a custom wall will be created in Gazebo that mimics the pool environment, in which various colored balls will be added to help develop and refine the navigation and collection algorithm. The ROS to Gazebo integration makes it possible to rapidly prototype virtually before physical implementation.
All the sensors and motors in the USV will be controlled using the Raspberry Pi. The control subsystem employs a line of sensors around the vehicle with a camera. The sensors combined with the motor and the propellers allow the USV to detect or avoid objects, navigate obstacles, and avoid collisions with walls. And the AI will send commands to the motors via ROS2, which will translate into electrical signals by the motor drivers, which control the motor's speed and direction. The boat is controlled by two propellers connected to motors and an IMU for navigation. The IMU helps with the positioning and the orientation of the vehicle in the water, and the AI will communicate with the motors through ROS2. The AI will receive real-time data from the servers and sensors and process it using various algorithms as mentioned as part of the recognition system. Based on the acquired data, the AI will determine what motor action is most suitable, such as moving forward or backward. Objects will instruct the motors to turn the USV to move to collect or avoid the balls and obstacles. When a ball is in front of the USV, the collection system rotates a cleated conveyor belt with the use of a motor to collect the balls into a basket. And after the collection basket is full, the vehicle will navigate towards the collection point and dispose of the collected balls.
In this first phase of our project, we have completed the initial research, conceptualized the design and selection of key hardware and software components of our autonomous USV. We have finalized the three major subsystems and identified the necessary components for our USV. Additionally, we are in the final stages of selecting suppliers for ordering and obtaining the required materials and electronics. Moving forward, our next step is to begin detailed CAD model of our USV. This will allow us to refine the structural design, validate the placement of the components, and ensure that the robot remains within the competition's size and weight constraints while maintaining stability on water.
Moving forward, our next step is to begin detailed CAD modeling of our USV. This will allow us to refine the structural design and ensure that the robot remains within the competition's size and weight constraints while maintaining stability on water. We will begin by simulating the robot's environment on Gazebo to fine-tune autonomous movement and obstacle avoidance. Moreover, we will begin with prototyping and testing of the USV and recognition subsystem using AI-based algorithms to detect and classify the colored balls. By following this structured approach, we aim to develop a fully functional autonomous USV capable of effectively performing the competition tasks. We will continuously test and adjust various aspects to ensure a smooth and reliable operation. We are confident in our ability to deliver a well-designed and efficient robotic solution.